And now for our last speaker before the poster session. So Dominic Masters, who is a lead scientist at Graphcore and is working on making physics-based model and GNNs faster.
Hello, everyone. So yeah, first of all, thanks to the organizers. Yeah, we've come all the way from the UK for this. And yeah, we're very pleased to be in sunny Montreal. It was much colder last time I came, so it's really nice. And yeah, it's a really great event. So I am from Graphcore. As a company, our core business is we make silicon chips to accelerate your machine learning workloads. Now I have a really nice job at Graphcore where I'm part of the research team where, essentially my job is just to do some cool stuff for this. My particular interests and the interests of my team around GNNs and molecular machine learning. So sometime last year in the summer, we were kind of working out what our big projects we wanted to do. And this OGB large scale challenge had already run one time the previous year. And we thought, you know what, maybe that's a good thing for us to do. Maybe let's enter this competition. So we gave Dom a call and we're like, hey, do you fancy collaborating on this? And we built this team of Graphcore, Valence, Mila engineers. And we actually did very well. And we went and won the competition and greatly exceeded our own expectations. So today, I'm going to give a little bit of an overview of what we did. But the main thing I want to focus on is some of the lessons that we learned, because we think some of them are really useful for thinking about how we're going to scale up these molecular machine learning models even more. And I think we learned a lot of really useful things. So first, what is the OGB large scale challenge? Well, the Open Graph benchmarks started as a group of in 2020, a group of 14 kind of small graph data sets. They were great because they kind of had a lot of breadth, but in reality, when everyone looked at them, they just weren't really big enough to support the kind of large machine learning models that we're interested in. So in 2021, they released this 3 new data sets from the large scale challenge, and along with that, a formal competition, where they have a fixed deadline, and then they're going to evaluate all the models, and they're going to have announce a winner. This has got loads of interest, and we've had submissions from people like DeepMind, Microsoft, Tencent, lots of really big labs across the world, and it's set into these 3 problems. One is this graph level task that I'm going to be talking about today for predicting molecular properties, this link level task, and then this node level task. So this is the one I'm going to focus on today, and the one I think is of interest to the audience here. So what is it? So the task is that, so the data set is essentially a large set of molecules where you give you the homo-LUMO gap as predicted using density functional theorem. Now, as a machine learning practitioner, that's great. I just see, I have a molecule, I have an answer, and I'm going to build a model that's going to kind of do that. But for people that care about DFT, DFT is just essentially really expensive. So the benefits of replacing it with really fast machine learning models, is very obvious. So taking it down from maybe tens of seconds, minutes, maybe even more than that, down to, our final model was doing 17,000 a second on a single chip. In total, there are 37 million molecules in the data set, where 3.4 million of those are available for our training. And then the performance is just a simple mean absolute error across the validation test set, and that's what we'll kind of using as our metric. So what did we do? So we built this model GPS++. I really want to stress that we have a poster of this over there, so I'm going to give a brief overview, but for for any of the details, please come see us our poster that's going to be at the next poster session. But the kind of core element of this is that we chose to build a hybrid GNN and transformer. This is built on work that's from Dominique's team before on kind of doing this hybrid model. Where we're going to do this in parallel, and hopefully we're going to get the benefits of both of those different strategies of kind of the inductive bias of a GNN and the all-to-all global communication you get from a transformer. Now, we were really keen on kind of very much focused on this MPN element, and it's really it's got about 70% of our parameters, and we've got this really quite complex structure that we've got where we're going to explicitly model some of the edge features, have a small global component, and essentially have lots of connections between them to try and allow it to learn as much as it can. And then for the self-attention, we also tried to give it some of the inductive biases that have been beneficial, things like Graphformer and Transformer M. So we're going to try and still have some of the inductive bias in that. Now for the rest of the model, we're going to have a whole load of these input features. This is kind of quite similar kind of strategy to what other people have done. And I'm going to have a range of loss features that are going to not just try and focus on the task at hand, but also do some denoising, which has again been found to be quite popular with these kind of models. So in terms of the results, so these are the competition results. And as I said before, we managed to win this. And this is our kind of, the competition is where we're not just going to run the model, do a single model. We're really going to do every trick in the book to try and get the best result possible. So here we actually ensembled about 100 of our models to get the best result. But then when you look at the kind of single model performance, we find that compared to the alternatives out there, we really do very well. I'm going to dig into those results a little bit more as we go through the lessons we learn. So we've got 3 broad lessons that we think we learned from this, that we think are interesting, but also really useful for the community and for other people to kind of take when they think about their molecular machine learning models, particularly at scale. So the first thing is that there's been a really, really strong trend over the last year or two to use transformers for these molecular models. They're quite nice because you haven't got too many atoms, so maybe about 20 atoms or so, which kind of makes global attention feasible. If you were going to really large molecules, that becomes very expensive, so there's been this trend to do that. And what we've seen from the literature is that practically every single model that has been targeting this data set has been a transformer. And what we've found is that actually the message passing methods have worked really, really well. And we want to put some focus on that and really say to people, you know, don't discount these. So looking at the results, so for the PCQ data set, we're looking at about 20 heavy atoms. So we've got some results here. And essentially what we see is that our GPS++ models are, you know, do the best. And you can see above that, pretty much everything is a transformer. And then the thing that actually really, really surprised us is that actually when we took the global attention element out of our model, we still did really, really well. And this can be seen on the bottom plot. So the blue line is our hybrid GPS++, and the orange one is if we just do the MPNN, we take away the attention. And so that makes it faster because they're doing less compute, but actually it really holds a lot of its accuracy. And so this is something that really surprised us. And you see the top of this table. So with the data set, you get some 3D positions. And the 3D positions are really important because that's something that in DFT is a really big core of how you calculate results. But actually, we found that even without those 3D positions, the GNN model actually did the best of all of them. And that really highlights the benefit of that inductive bias that you get from those GNNs that is actually quite difficult to put in the transformer. So when we're thinking about this at super large scales, I've kind of put together 3 potential explanations, hypotheses. This is absolutely not exhaustive. And this is really some thoughts of mine that I think trying to motivate what might happen as we go to much bigger data sets and much bigger molecules. So, and in terms of, so one explanation is just the inductive bias of that strong GNN component is just super, super important, particularly at the scale that we're looking at. But what you would take from that is actually if you go to a much larger scale, so you increase your data set by 10, 100 times, maybe that's something you can learn. And I think that's a really interesting question. Does the flexibility of transformers become more important as you go to those really big scales? That's something that from other areas seem to be a trend. Another one, global attention is beneficial because what it allows you to do is to model the global interaction, so the long-range interactions between atoms. So you've got a long string of atoms in your molecule. There might be some, is there some interaction between the ends? That's essentially quite hard to model directly in MPNN. Maybe it does something there, but it's quite a simple thing for a transformer. So essentially, as your molecules get bigger, maybe the transformer element becomes more important, but it also becomes more expensive. So again, some really interesting questions that I know I'm very interested in, and I hope other people have interested in and thinking that. And then the last one is that maybe the fact that with GNNs, we get to explicitly model the edges themselves, maybe that's a really beneficial thing. And that is something that with a vanilla transformer, it is very hard to do. I know there's been some attempts to do that with kind of this GEM2 model, for example, but maybe that's a really important element. And if that's the case, then actually it would suggest that MPNNs are maybe even going to be better and beneficial even at scale. So I think what we see from that is there's lots of questions there and lots of things that I think yeah, really valuable to take forward. And if we just focus on transformers, I think we'd miss a lot of this stuff. So, next lesson. Next lesson was that speed was really key to success in this. And while in a competition environment, that's kind of obvious because it's a time-bounded thing, but I think this is also something that everyone will feel in the research community at the minute. Everything moves so quickly, you know that if you don't execute quickly on one of your ideas, the reality is that someone else will probably do it first. And so I think this is, and at Graphcore, where we want to, our whole aim is about speeding up your ML training and inference workloads. This is something that we really think is super important and something that we really want to kind of help the community with. So, and when I say speed, it's not really the speed of your model, that is a part of it, but it's the speed of iteration. You want to be able to go away, run something, and have a whole load of results, overnight that you can then go and interpret, and that really helps with the progress of your project, particularly at, with anything you're looking at. So to kind of highlight that, I've got this plot. So this is a kind of typical weights and biases plot. Now this is every model that we ran throughout the whole of our competition. So there's over this 3-month time scale, we ran over 6,000 models. And you can see kind of really interesting trends where we start off at a kind of reasonable MAE. We really focus on, actually at the start, we really focus on much smaller models to, again, increase our iteration speed. And then as we kind of get through, we kind of keep going down. And another really interesting part is that the published state of the art changed multiple times throughout the competition. So the ability to pivot and to move quickly was absolutely critical to our success. And in terms of enabling that, one of the things that we had as a core of our team was really trying to build fast and performant models right from the very start. So we did that by exploiting the acceleration from IPUs, but also really focusing on distributed training, low precision arithmetic, all those things that we know can speed up our model training. And with that, so these numbers are quite hard to get exact figures for, but we think that we train that for our state-of-the-art models, we would train them about 5 to 10 times faster than the equivalent transform on GPUs for an equivalent system. So you can see how that speed benefit, if that's kind of every day, it's going to make a really big difference to how fast you can work through all your questions or your bugs or your hypotheses. And that was really a really big benefit in our work. And as I said before, the color in this plot is the size of the model. And as you can see, we really focused a lot on doing as much as we could with small models. We were able to run kind of hundreds of training runs a night. You go away and then you come back and it's a really nice place to work in. And this is something that obviously we want to enable for as many people as we can. So I've talked a bit about this acceleration. I've said that we've done this with IPUs. So I'd like to take a minute just to explain a bit more about how IPUs work, how they're different to GPUs and what this and how they help. So one of the fundamental differences about IPUs is about how our compute and memory is arranged on the surface of our chip. So for a GPU, you've got lots of off-chip DRAM, and you're going to have mostly compute on your chip. Now for us, we're going to distribute all of our processors. So every red dot is a processor, and then we're going to co-locate the memory with it. And we're going to have a lot of really fast on-chip SRAM, and then we're going to split this over 1,472 separate cores. What this means is that we can access every bit of memory at extremely high bandwidth, so 65 terabytes a second compared to maybe 2 terabytes a second you would get from HBM. And the fact that we have all of these 1,472 cores in what we call a MIMD architecture, so multiple instruction, multiple data, opposed to single instruction, multiple data, means we're really effective exploiting parallelism. So when things aren't just a big matmul, we can really exploit the parallelism there, and that's really beneficial. And the really high memory bandwidth, of course, really helps with operations at memory bound. And this kind of complex structure with memory bound operations is something that we really get a lot of in GNNs. So we did a little bit of work to try and benchmark these things. And in terms of the GNN compute, I think we can characterize them as, for one, having frequent use of gather-scatter operations. So these are sparse memory access ops, which are inherently memory bound. So that's one thing. but also that the arrangement of map malls is often more complex than you'd have in a big transformer. So you see in our model, we've got a small MLP on each of our node, edge, and global features, which and inevitably they're going to be much smaller. So you're going to have more smaller ops. Now, this is quite a hard thing to accelerate on a GPU, but it's something that the IPU performs very well at. So then we kind of compared these individual ops against an A100. So the blue line, this little, just a histogram. The blue line is the gather. The orange line is the scatter, and you can see that we have between, about 2x on a lot of them, but up to as much as 20x improvement over A100s. And then when you put that in a message passing block, so this one is as a SNET, we get about 5x improvement on average for a single chip. But then the benefit is that our chips are actually much cheaper. So, you get about a quarter of the price you pay for them in the cloud. So you can get some really significant benefits in terms of a kind of per dollar over kind of GPUs. So, of course, it's one thing us in-house doing all this work and making this fast, but it's really important that we try and enable that for as many people as we can. And I think particularly academic communities like this are the ones where we really want to inspire people to try and pick up our hardware and do something interesting. So one of the lessons we had is that building the software for this project, it was hard. Like, we had a really dedicated group of engineers doing it, but it was hard. It was error prone, and actually for molecules specifically, things like the input featurization is really difficult, and it's difficult to test. So the kind of obvious way to improve that for everyone is by having better open source software. And this is something I know Valence are doing with the MolFeet package that they've got a poster for, and something actually working in collaboration on a kind of full training library for molecular models that we really want the whole community to use, and that will focus on having really highly accelerated, enabling really high acceleration, and making a lot of those things difficult. So a lot of those things much easier. Okay, 5 minutes, cool. And on top of that, IPU is now available in the cloud. So if you're interested, if you're interested in using them for some of your work, please go have a look at, speak to the people on our booth, and these are things that we have programs for helping students and things like that to do that. So last lesson, and this is one that is kind of interesting because this is a large scale challenge. So it was really about building the largest data set we could, or that they could. And the PTQ data set is really very large in terms of effort, the effort it took to create. It took about 2 years to create it. But when it comes to machine learning, this 3.4 million training samples really just isn't big enough. And you can see this by looking at kind of all the state-of-the-art results, and the model sizes just aren't that big compared to the kind of things that we see in NLP. And I can tell you for sure, I know we did, and you see evidence of it in other people's open source software. Everybody tried to make them bigger. That was an obvious vector for improvement in this competition, and no one is able to because you just overfit. So one of the really key elements and really key lessons is that the data sets just need to be larger. And I think there's a whole load of ways you can do that. And I think open source collaboration and things like that is definitely one. One way that we are doing that from Graphcore side is to think about how we can speed up the DFT at the core of creating that algorithm. And this is another one we've got a poster from. Alex down here has been the lead on this, where DFT libraries, in essence, are essentially very hard to accelerate. So all of the kind of molecular data sets like PTQ, Chrome9, AN1, were all created using CPUs because they're really hard to accelerate on GPUs. And what this has led to is just that the data sets are not big enough to work with the models, the kind of size of models that we're really interested in. Now, with IPU's really flexible MIMD structure, actually, it is really amenable to a lot of the complex algorithms that they want that we're kind of solving for in DFT. And this is something that we were working with the aim of being able to train to 1 billion, to have a data set of over 1 billion training examples. And we think that's the kind of level where hopefully we can build the kind of scale of models that I think everyone is really interested in. We've got a small example here of what happens when we train just a 9 million parameter SNET with up to 100 million parameters and 100 million data samples. And as you'd expect, the model gets better. And as I said before, we've got a poster on that, so please do come ask some questions. And then with the game, where we can do this all in the cloud, such that essentially everyone can create a data set. We want it to be cheap enough and accessible enough that everyone can create a data set, and this is really great for active learning or things where you actually want to investigate the process of creating data set itself. And we think that's a really important part of this, because up until now, we've had these very static data sets like PCQ, where all the parameters that, the complex parameters that you need to define when doing your DFT, you can't go back and change those. And we just really don't know the impact of that on our final model. So that's everything I've got to say. We've got a poster on GPS++ in the first session just after this. We've got a poster on the DFT after that in the second session. And then we've got a booth over here. It's not quite as fancy as the one I've got a picture in, so you kind of have to imagine that, but it's just over here. So please talk to us about how you can get access to IPUs. Okay, thanks.